Hello, I'm the meditative Mr. Daycock, and today I'm going to be teaching you how to solve second-order differential equations where the particular integral has a term in common with the complementary function. Okay, so here we are. Find the general solution to d2y by dx squared plus 2 lots of dy by dx minus 15y equals e to the 3x. So as always, what we want to do first is find the complementary function. And there's a very good reason why we do it in this order. So we want to find the complementary function. So we are going to solve m squared plus 2m minus 15 equals 0. Now this factorizes nicely to m minus 5, m plus 5, m minus 3 equal to 0. And that gives us m equals minus 5 and m equals 3. And so we get our complementary function of y equals a e to the minus 5x plus b e to the 3x. Now, we want to try our particular integral. And for our particular integral, we want to try y equals a e to the 3x. But, and this is the whole point of the video, this and this are effectively the same term. So if I were to try something like that and add it on, effectively this particular integral would just disappear. Now, as always, if you have any kind of problem like this, where the particular integral, well, where any time we have a term repeated, but we want them to be different, you just multiply it by x. So we're going to try instead y equals x e to the 3x. That gives us dy by dx. Here we have to use the product rule. So we're going to get a e to the 3x plus a 3a x e to the 3x. And then d2y by dx squared. And if you're not sure about this, I have a video on the product rule. So check that out. And we're going to get 3a e to the 3x plus, and we're differentiating this with the product rule again, so it's going to be 3a e to the 3x plus 9a x e to the 3x. And these two terms came from this term using the product rule. And then we're going to plug that in. So we're going to get, well, these two terms combine nicely just to 6a e to the 3x. So our dy by dx term is going to be 6a e to the 3x plus 9ax e to the 3x. Then our dy by dx term is going to give us plus 2 lots of a e to the 3x plus 3a x e to the 3x. And then lastly, that we've got the minus 15 lots of, and that's this term here, a x e to the 3x. And that needs to equal, well, we just had on the end e to the 3x. Now let's do some expanding and simplifying. So we're going to get 6a e to the 3x plus 9a x e to the 3x. That's just the first bit again. Now the expanding part. So we get plus 2 lots of a e to the 3x plus 6a x e to the 3x minus 15 ax e to the 3x. And that needs to equal e to 3x. Now if we notice, 9ax e to the 3x plus 6ax e to the 3x is 15. So in fact that and this all cancel out perfectly. And we are left with 8a e to the 3x is equal to e to the 3x. And that gives us that a must be equal to 1/8 by comparing coefficients. And there we go. So we get our particular integral is going to be y equals 1/8 of x e to the 3x. And notice this is working out really nicely, and this should emphasize, and it makes sense, not a proof, but it emphasizes it should make sense how all these terms with the extra x in all disappeared. So if it wasn't a repeated solution, that wouldn't have happened. And so having that extra x there would have got in the way, but in this case it didn't. And so we get our final solution, our general solution, which is equal to our complementary function plus our particular integral, is y is equal to a e to the negative 5x plus b e to the 3x plus 1/8 of x e to the 3x. And there you go. Right, one more example. And I'm going to move this. Now we're just going to work down across the side here. Solving this, find the general solution of d2y by dx squared minus 7 dy by dx equals 5. And we get m squared minus 7m equals 0. This is, of course, our complementary function solution. And that tells us that m is equal to 0 or m equals 7. And so we get our complementary function as y equals a e to the 0x plus b e to the 7x. But of course, anything to the power of 0 is 1, so this actually is y equals a plus b e to the 7x. And that's very important. And now for our particular integral, well, we want to try y equals just some constant, so say c, but notice we've already got a constant in our complementary function, so in fact we're going to try y equals a constant times x, so cx. Okay, and we want to plug that in, so we get dy by dx is equal to c, and d2y by dx squared equals 0. Plugging that in, and we're going to end up with, from this point, 0 minus 7 lots of c, because we're plugging in dy by dx as c, and there are no y's, so we don't need to plug that in at all, equals 5, and that tells us that c has got to be equal to negative 5/7. And then we're done. That there is our complementary function, our particular integral, and we have our complementary function, so y is equal to a plus b e to the 7x minus 5/7 of x, because remember our particular integral was cx, not just c. And there we go, we're done. That is how you solve them if we have a term in common between the two, so a constant, or maybe each one has an x squared, or each one has a cosine 2x. If we had a case where one of them we had, say, cosine of x and cosine of 2x, that would not be in common, because these are very different terms, and so you would not need to multiply by an extra x there. Equally, if you were to have e to the 3x cosine of x and cosine of x, even though you've got the cosine, this here completely changes the term because of the e to the 3x. So it's the entire term, bar the multiplicative constant, that needs to be in common for you to require this extra x. Okay, thank you very much for watching, and I'll see you in the next video.